Hi, today I want to define functions, the big moment. Certainly a concept you've seen before in college algebra and pre-calculus, but now we have our logical foundation of um, symbolic logic, right? Quantifiers. And so I want to frame functions in terms of this language of symbolic logic. So what is a function? It's a special kind of relation, right? A function is a relation that satisfies a very particular property. So we have ordered pairs, right? One chosen from a set A, one chosen from a set B. So it's a relation R. That's right, a subset of the cross product, right? A subset of A cross B. And it is called a function if and only if for every element little a in A, there exists a unique element B in big B such that A is related to B. Right, this is our definition of function. And notice I said the word unique in there. So that's the way that is notated is with the exclamation point. You still write there exists, but then you put an exclamation point afterwards. Here it doesn't mean factorial like it does in some other contexts, right? If there were a natural number before that, you typically call it a factorial. But here it's there exists unique. That's how you read that exclamation point. It's worth noting how to write that, the uniqueness, in terms of just regular quantifiers for all and there exists without the exclamation point, because it's quite tricky. So here's what you would say to say there exists a unique element. You'd say that for all A in A, there exists a B such that A is related to B. So this first part just says there's at least one, right? There's at least one element B paired with that's related to A, that's paired with A. But how do we know there aren't more? Well, here's how we get there to not be more. We say, and what? And if you find other elements, say some C, right, in B that are also related to A, then you know what C must have been? C must have been just another name for B, right? That C, if A is also related to C, then C must actually be B in disguise, right? B and C must be equal. So that's how to get this uniqueness condition expressed in terms of quantifiers, or ordinary quantifiers for all and there exists, right? So you see now why why the exclamation point is a useful notational shortcut, because it kind of takes a while to say uniqueness without it if you just want to express it in for all and there exists. So to think about this a bit in terms of a diagram, right, we can say that here is our set A, here is our set B, right? And the relations can be represented this way, where elements A over here get shown as having an arrow to some element B, and that's what indicates this relation R. So that arrow relates that A is related to B. Now, this uniqueness condition, a nice way to visualize it is, hey, if there were some other element over here, C, such that A was related to C, then what is C? In reality, it is not this, right? This is not what happened. But instead, what happens is this arrow in reality is just pointing up here to B again. It's just a duplicate drawing of the same arrow that we already drew, right? That C and B cannot be distinct elements. So that's a way that you can say, that you can express uniqueness, right? So this is how the blob diagram would look for the arrow diagram for expressing a relation that is a function, right? You can basically, you could never have two arrows coming out of the same element in the input space on the left hand side, right in set A. So, all right, so some related vocabulary, right? In this case, these are the set A is called the domain, right? The domain of the relation R, right? Which R is a function, right? And the set B is called the codomain, right? So the domain represents the set of all inputs. The codomain represents the set of all possible outputs, right? Note, one thing to note here is note that not every element of the codomain has to actually get used. Some of them might just be sitting there and never that an element A is never paired with it. An element of the set of the domain never gets paired with it. That can happen. You're just sort of specifying the set of all possible outputs. Right? So because not every element needs to get used, we then define the range, right? So the range is the set of all elements that do actually get used, that are the set of all elements in B that actually get paired to. So the range expresses this idea. The range, which often we write range of R, right, this is the set of all elements in B such that there does exist an A in A with A related to B, right? This is the range. So that's the set of all elements that actually get used. So you can imagine it this way. You have A is the domain, right? You have B is the codomain. And then you have all these A's get mapped to B's. So this A gets mapped to a B. Maybe this is, A1, A0, say A1 gets mapped to some B1. Maybe A2 also gets mapped to B0, right? I never said two inputs couldn't get mapped to the same output. It's that one input can't get mapped to two different outputs, right? And so on. So then this subset, right, is called the elements that actually get used. That subset is called the range of your function, right? Range of R is the set that actually gets used. Maybe you have some element out here, B5 or something, right? And maybe B5 never gets mapped to, right? There are no arrows that come into B5 from anything in the domain. So then B5 would not be in the range, right? It would be in the codomain, but not in the range. So this is the language that gets used here. Now, notationally, right, for our functions, we tend to not list everything out as ordered pairs, or we don't want to always have to list things as ordered pairs, right? Like here, I'm doing A0 with B0, A1 with B1. I put A2 back to B0 again, right? You can just list out ordered pairs for your to specify your function. You can draw these arrow diagrams to represent your function, but these in general are not the most common notation that we use for functions, right? Often we try to use a different notation, right? The notation that you're very familiar with in pre-calculus or college algebra, right? So if you call F the relation, instead of calling it R for relation, call it F for function. And if you have some element A that's related to some element B, then we tend to write F of A equals B, right? This is how we typically like to denote our functions in, say, college algebra, in pre-calculus, right? This is kind of our favorite way to do it. So this is a common notation. I do want to show, however, some other notations. This one is very, very, very common if your inputs is the real numbers or some subset of the real numbers, right? This is the context that you're typically working in the context of college algebra, pre-calculus, right? Where your inputs come from the set of real numbers. But you can also have subscript notation, right? So if A is instead the natural numbers, right, or some subset of the natural numbers, instead it's very common to write the input as a subscript instead. So you could write it as you'd call the little n the inputs. And if you write it like this. If n is related to some element a sub n, then you just write you write just that. You write a sub n equals the output, right? This means the same thing, right? So instead of a of n, right, you could write a sub n. So this would be equivalent notation to saying this, a of n, right? If the function gets called a, right, in the context of a sequence, this is very common. There's also another common context, especially if there are only finitely many inputs. Then often we write a function in a table. Right, and that table just has a row of inputs in the top, and then the corresponding outputs in the bottom. So that there you would list, A and the corresponding B, right? So say A0, B0, A1, B1, A2, B0, right? This would be representing this same function that I showed up here, right? These three arrows that I showed up here, that would be a way of representing that in a table. So I'm just listing inputs and outputs. So especially if you have finitely many inputs, it's very common to represent a function like that, where you're just showing the top entry gets mapped to the bottom entry for each column in the table. So, all right, so let's look at all of this in a few examples. We're not really going to do a lot of math here. We're just getting used to the new language. So, for example, let's consider the relation R equals divides. So is divisible by, right? And this is right, a favorite example of a relation on the natural numbers. Right, so another way to say that is A is related to B if and only if A divides B, right? If A divides evenly, if one natural number A divides evenly into another natural number B, then we say A relates to B with this relation. So here you could represent this as a relation from the natural numbers to the natural numbers, right? And you could say what this does, right? You could say, okay, 0. Let's not even worry about 0 for the moment. You could include 0, but we don't even need to. We don't talk about 0. So here you could say, for example, 1 divides 1, 1 divides 2, right? Right there, not a function, right? This is a valid relation. Divisibility is a perfectly valid relation. It's not a function because of what I already saw. Just those two arrows right there, right? You can say 1 divides, so notice that 1 divides 1 and 1 divides 2. So this relation, divisibility, is not a function because there was not a unique element that 1 related to. It related to 2 different elements. And in fact, it actually relates to infinitely many elements. And in fact, actually all of these relate to infinitely many. For example, 2 relates to 2, but then 2 also relates to 4 and so on, right? So this is just spectacularly failing to be a function, right? Perfectly good relation, not a function. So that's an example of a relation that is not a function. On the other hand, let's consider this relation, also on the natural numbers, let's consider another relation R on the natural numbers by A is related to B if and only if A is equal, if and only if B is equal to the square of A, right? Say this is our relation. If B is equal to the square of A, then we say that they're related. A and B are related. This, if you think about what elements here are related, so what would the element 0 be related to? Well, if 0 is the input, I want for 0 to be related to B, I need 0 squared to equal B, right? That's the only way that 0 would relate to B. If only if B equals 0 squared. Oh, so I need B equal to 0. So this is the only arrow that gets drawn for 0. Right? Now, how could 0 relate, how could 1 relate to something, some B? Well, the only way 1 could relate to something is if B equals 1 squared, right? Meaning B has to equal 1, right? 2 relates to B. Well, that's if and only if B is 2 squared, which is 4. Right, so 2 would go to 4. And so on. 3 would get into 9. And on and on and on. Right, so this is representing this as an arrow diagram. Now, if you notice, some of these elements don't get hit. For example, 3. No one goes to 3. Right? 2. No one goes to 2. Right? Those do not get used. So this is a good example where the codomain that we specified and the range are different from each other, right? So in this case, we would say that the domain and codomain, those were both the natural numbers, because I said it was a relation on n, right? And when you say a relation on a set, you mean that you're pulling ordered pairs from that set across itself, right? So we knew we had, by definition, R was a subset of n cross n, right? But the range is not equal to n, right? What is the range of this relation? The range here is only the perfect squares, right? 0, 1, 4, 9, 16, etc. Right? Another way of saying that is it's the set of all numbers a squared, where a is a natural number, right? So take the set of all natural numbers a, and then square them all, right? And then you get the range of this function. So this relation R is a perfectly good function, right? So we even found, which I never wrote, right? So this R is a function, right? And not only did we figure out that it is a function, but we found the domain, we found the codomain, and we found the range. So this is an example of a relation that is not a function, right? Here's an example of a range that is a function. And in each case, we were able to identify the domain. In the second case, we were able to identify the domain, the codomain, and the range, right? In the first case, we didn't really care to identify any of those things. It wasn't a function, so there was, so we didn't even ask for range or codomain. Range, domain, codomain, or range, right? All right, thanks. So that is there we have some of the fundamental definitions expressed in symbolic logic of what it means to be a function, which uses this idea of uniqueness. It's actually kind of tricky to express with codifiers, right? The idea, the elements, the vocabulary, domain, codomain, and range, and a few ways to represent functions, right? You can use these arrow diagrams. You can use sequence notation, which we'll see a lot of that down the road in this course. Table notation, which also we'll see a lot down the road, especially when we study permutations. It's very common. permutations on finite sets, and then an example of a relation that failed to be a function and a relation that succeeded to be a function. All right, great. Thank you, and I'll see you next time.